Alrighty, hello everyone. Welcome to part 3 of the section 3 of mathematical proofs. So we will begin looking at our last two topics in this section, and the last proof technique we'll learn in this section 2, which is direct proofs. So continuing from part 2, direct proofs are based on implications. So just writing out an example of an implication there. Sorry, that needs an extra parentheses. There we go. So, a direct proof shows that for two open sentences, say Px and Qx, over a domain, let's call it S, if we assume Px to be true for all x that is in our domain, we can show Qx to be true for all x that's in the domain. This proof technique is the most commonly used in mathematics. So let's look at an example of a direct proof. So let's say we are given this proposition: if n is an even integer, then 3n plus 6 is an even integer. So before we try to prove this statement, let's look at how we can define even and odd integers, because they'll probably come up pretty frequently. So this is kind of an easy way to understand. So the domain S would be 2k, where k is an integer. And of course, this would imply numbers like -4, or this would include numbers like -4, -2, 0, 2, 4, etc. And then odd integers, the domain S would be, let's differentiate these two. Let's call the domain T would be 2k plus 1, where k is an integer, and this would include integers like -5, -3, -1, 1, etc. So, knowing that, we can write our proof. So just to scroll back up, if n is an even integer, then 3n plus 6 is an even integer, is what we are trying to prove. So let's start off by saying let n be an even integer. Since n is even, we can write n equals to k, where k is an integer. So n plus 6 equals 2k plus 6, which equals 12. Don't know what's going on with all these squiggles. Which equals 12k plus 6, which equals 2 of 6k plus 3. So, therefore, 3n plus 6 is even as desired. So by assuming the first statement that n is an even integer and letting it equal 2k, we were able to plug it in to our second open sentence, and we were able to show that by the second open sentence being a divisor of 2, that it is even. And writing as desired is often a good way to close a proof, as I know I probably didn't mention that in the proof writing, and you didn't see that in the trivial and the vacuous proofs. So, all right, that's pretty much all we'll look at for direct proofs. So, now let's look at some proof settings or conditions. There are different settings and conditions that we will encounter in math. We will look at and understand a few before we start more proof techniques in section 4. So, one proof setting or condition you might encounter is divisibility of integers. So, if we have two integers say A and B, if A does not equal 0, then A divides B if we have another integer C such that B equals AC. So the notation for divisibility is just a line, straight line. So if we were going to write A divides B, we would do A, then draw our line B. And then this is for when they do not divide. So A does not divide B would equal A does not divide B with our line and a slash through it. So we can define integers by multiples and divisors using remainders. So if we had a multiple of 3, then every integer can be expressed as 3q plus 1, or 3q plus 2, where q is an integer. And this is similar for 4. You can write 4q plus 1, 4q plus 2, or 4q plus 3, where q is an integer. All right, so now we will look at congruence of integers, or this might also be known as modulos. So for integers a, b, and n is greater than or equal to 2, we define a as congruent to b modulo. Just going to underline these because these are important words to understand for this topic. And if and is divisible by a minus b. So the notation for this is A is logically equivalent to B mod N. Here's some definitions to understand for this topic. So we have congruent, and this is when two figures or objects have the same shape and size and modulo. And this is a math operation when the remainder of one integer is divided by another. So an example of this would be 19 is logically equivalent to 3 mod 8, since 8 is divisible by 19 minus 3, or 8 is a divisor of 19 minus 3. Sorry, I've been saying that wrong. So, then we have 20 is not logically equivalent to 5 modulus 4, since 4 is not a divisor of 20 minus 5. Alright, so that's it for congruence of integers. Now we'll change colors because we have another setting to look at, and that is real numbers. So, if you recall, this was early on in section 1 where we covered sets, that real numbers are equivalent to R or some symbol where it represents either an a rational number and an irrational number. So some properties we will want to look at or prove with real numbers involve multiples, absolute values, and inequalities. So, an example say we are given this proposition: if x is a real number where x is not equal to 0, then 2 is less than or equal to x, which is less than or equal to 4, implies that 1 over 8x is less than 1 over x squared plus x. So a great way to work out these types of problems, and especially ones that involve inequalities, is to start with some scratch work. This is kind of like involving a section where you have a proof strategy for a proof, except this mainly involves just rewriting things or solving things. So this is our inequality. So let's do some algebra here. We cross multiply the, or when we multiply the denominators with the numerators, we get this. Then we subtract 8x. Then we can factor this out. So this is true because of our boundaries. So if you were to plug in 2, 3, or 4, or any number in between into our inequality, it would be true. Or whatever number you would get would be less than 0. So we will use this scratch work to prove this statement. So let's begin our proof. So we're going to let our final result we found from our scratch work start our proof off. And let's make sure we define our variable slash symbol x, where x is a real number, and x is less than or equal to 4, so it follows that. Let's back work our steps from our scratch work. Sorry, it's supposed to be plus. And there we go. We just directly proved this statement, or this proposition slash statement involving real numbers. All right. There's 2 more things we will look at here, and then we will be done with section 3, at least for the notes, and then we'll have the examples, and that will be sets. So if you recall from section 1, we had intersections, we had unions, we had differences, these set operations, we had subsets, and everything else that we looked at. So sometimes we might work on proofs involving sets. So one important thing to remember when you work on these proofs is to recall the fundamental properties from section 2, which were in the logical equivalence topic. We had commutative laws such as A union B is logically equivalent to B union A. We had our associative laws, so A intersection of B intersection C is logically equivalent to A union B, or intersection B intersection C. Then we have our distributive laws. So A union B intersection C is logically equivalent to A union B intersection A union C. And then also we had De Morgan's laws. This was something like the complement of A union B is equal to the complement of A intersection complement B. So these will be handy when doing proofs with sets. And then the last setting we will look at is Cartesian products of sets. So, if you can recall from section 1 for two sets, A and B, the Cartesian product of A and B is equal to an ordered pair of A and B, where A is an element of A and B is an element of B. or a set of ordered pairs A and B from the sets. So note, if A is an empty set, or B is an empty set, then the Cartesian product of A and B is the empty set. So, an example of this: if A is a subset of B, then the Cartesian product of A and A is a subset of the Cartesian product of B and B. So, our proof strategy for this, let's use set definitions and directly prove that Cartesian product of A and A is a subset of the Cartesian product of B and B. So, let's write our proof for this. So let's let an order pair xy be an element of the Cartesian product of A and A. So if this is the case, then x is an element of A and y is an element of A. So since A is a subset of B, it follows that x is an element of, B, and y is an element of B. So, therefore, xy is an element of the Cartesian product of B and B. As desired. Let me try rewriting that square where it looks a little better. And you may be wondering, well, why did I conclude with x and y is an element of the Cartesian product of B and B and didn't write the statement we were trying to prove that the Cartesian product of A and A is a subset of the Cartesian product of B and B? Well, the reason being is that since we know that the order pair x and y is an element of the Cartesian product of A and A, and we showed it's a Cartesian product of the element of B and B, then we can imply that it is that the Cartesian product of A and A is a subset of the Cartesian product of B and B. So, all right, that is it for section 3. Thank you guys so much for watching. Well, at least for the lectures of section 3. In the next video, we will be doing some example problems, and then section 3 will be finished up. So, thank you guys so much for watching, and I will see you in the video for the examples.